Okay, hi guys. So I finally got permission from the host to record. So let's start our lesson today. So in this lecture, we are going to talk about perhaps a completely new concept to you if you've never heard of it. So it's not just about mod prime numbers, but a new kind of set, which I would call, or actually the actual name is called a field. Oops. So there is a very formal definition for a field, but after formally defining it, we will talk about the more intuitive way of thinking about it. So if you have your handouts, you probably need to open it up right now because the definition is quite long. So a field is a set equipped with two kinds of operations. With two kinds of operations. One of the operations is called plus or addition, and another operation is called multiplication. However, these are just names for now. So don't think of addition to be really addition in the real numbers or those sets that you actually know. I will just call these operations addition and multiplication for now. So what's an operation? An operation, well, in particular, a binary operation is where you take two numbers, you apply the operation, you get a new number. So if you have A and B, I can do A plus B. Or if A and B, I can do A times B. And that would give us a new set, a new number or a new object in that set itself. So that's what we call an operation. And the operation plus and times must fulfill the following properties. So first of all, commutativity and associativity. So A plus B plus C, like this. If we first add B plus C and then add A, the same thing as A plus B first and then add C. And the same thing goes for multiplication as well. In fact, if the context is clear, I will not write the dot if the context is clear. So that's associativity, and then commutativity is where you can swap A and B. So it's kind of like symmetric. Because not all kinds of operations actually fulfill this. For example, if you multiply two matrices, AB is not necessarily the same as BA, right? So these two properties restrict the kind of operations that you can have on such a set. And then second of all, you have what we call additive identity. Which, so let's say this field is called F, okay, or this set is called F. There's an additive identity inside called 0, or actually, again, this is just a name. This is just a name. Don't think of this 0 as the actual 0 in the real numbers or complex numbers or whatever. This is just an object in this set. So sometimes they write 0 and then subscript F. This identity is an element such that A plus 0 is equal to A for all A inside that set. Okay. And of course, there's a multiplicative identity, which is called 1. Again, I'll just write subscript F, even though if the context is clear, I can remove the F. So a multiplicative identity is where if you multiply anything in that set by this element, you'll get back the same element. And then the third is what we call inverses. inverses. So for each A inside that set F, there exists another element called minus A, when I say exists, it doesn't mean it has to be a different element. It could be itself, it could be another element. So this element, which can also be denoted as minus A, is called an additive inverse. It's an element where if you add those two numbers, you will get 0. And also there is a multiplicative inverse, but for all elements that is non-zero. So for all A, which is non-zero, so there's an extra property here. There exists something called A inverse, such that if you multiply them together, you get the multiplicative identity. And last but not least, you have to obey this last law called the distributive law, that A times B plus C is always equals to A times B plus A times C. So these are all very abstract because we are not talking about the regular sets that we know. We're not talking about the set of real numbers. We're not talking about the set of rational numbers. We're not talking about the set of complex numbers or anything that is similar to it. These are just abstract definitions for an operation plus and an operation multiplication. Okay, so if you have a given set of some random objects, but to each pair you assign the addition result and the multiplication result, so you have a lot of pairs. If you have n objects, then you have to kind of assign n squared for n squared values for addition, n squared values for multiplication. If you have such an operation that satisfies all of these properties here, I can call this set a field with the operation plus and multiplication. So of course, the set of real numbers, the set of complex numbers, they obviously satisfy all of these properties. So those are fields. So Q is a field. R is a field. C is also a field. Can anyone tell me why Z is not a field? The set of integers, why is it not a field? Yes, exactly. Not all integers have a multiplicative inverse, right? In fact, most of them don't. And of course, when I talk about Z, I talk about the usual addition and multiplication that we use. So under these operations, so again, when you want to talk about a field, you have to not just talk about a set, you also have to talk about the associated addition operation and the multiplication operation. Okay. And what's special about these three sets, Q, R, C, is that they are infinite. They are also what people would say dense. But there are fields that are finite. And the topic is about finite fields today. But of course, I will give reference to these other fields as well. So in particular, let's look at the case where the set given is 0, 1, 2 until p minus 1. Zero, 1, 2 until p minus 1. And well, if these are just a regular subset of the natural numbers, we would say, okay, p minus 2, this element, plus the element 3 would be p plus 1, right? But let's say we want to be sneaky and we just define addition in a new way such that p minus 2, this element, plus 3 is not p plus 1 anymore, but it's 1. So I talk about mod p addition. So mod p addition is obviously different from regular addition. I mean, it's somehow related, but it's completely different, right? For mod p addition, p minus 1 plus 2 is 1, but for regular addition, p minus 1 plus 2 is p plus 1. So that's why I said, don't think about this plus and multiplication as the regular, usual ones that we know for those popular sets. But instead, think of it just as an operation that takes two inputs. In fact, you can think of plus and multiplication as a function. So like a plus b is kind of like a function that takes two inputs, the add function, and then you have two inputs. But yeah, so let's say I take mod p addition and mod p multiplication. And also for clarity, let's just rename everything here to be 0 bar, 1 bar, 2 bar, p minus 1 bar, just to emphasize that we are not talking about integers here. We're talking about mod p numbers now. So now, for example, these two, like p minus 1 plus 2 is now 1, but of course with the bar on top. So these are like new objects now. They are like completely new objects that interact in a very different way compared to the integers. Okay, but mod p addition and multiplication, they fulfill the first rule. That's fine. It's quite obvious because we know that this kind of mod p addition and multiplication kind of derives from the regular addition and multiplication. So, and since you're already familiar with modular arithmetic, you can probably see why the first rule is true. And the second rule, so is there an identity? Yes, it's this 0, right? This 0 is the additive identity. And then the 1 is the multiplicative identity. And 3, the first rule of 3 is obvious. So if you have k, then take p minus k. Now, let's skip this rule first. Multiplicative inverse. We'll come back later because it's not that obvious that it exists yet. But let's look at 4. This one's also obvious. Well, if you know your modular arithmetic. So what remains to show is that this thing is true. Is it true? Does every non-zero element here have a multiplicative inverse? So that's our first question. And in fact, there is a nice theorem about this. Okay, someone said yes because of primitive roots. Okay, that's a bit too advanced, but you're right. If you talk about primitive roots, then you can get that easily. But let's say we don't know about primitive roots, and in fact, let's say we don't know about primitive roots. Is there a simple way to prove that every single non-zero element in this set has a multiplicative inverse? In particular, after multiplying by it, it becomes 1. So what I'll do is this. Let's say A is, well, let's say it's not 0. And it's a part of this set. Now, I multiply everything by A, right? I multiply everything by A. I'll multiply everything by A. 0 becomes 0. Okay. It might not be that clear. Why? Oh, but no, but we're talking about mod p multiplication, so it is 0. 0 times a mod p is 0. 1 times a, I'll just write a bar, but I think you can just say it's a. I mean, it depends on how you want to name those, but I'll just put a bar. And then 2a. Now I'll just write a and then 2 like that. Then 3 bar a and so on until p minus 1 bar a. So remember, we're talking about mod p multiplication. Now, I claim that this only permutes the elements. So basically, 1 goes to somewhere else, 2 goes to somewhere else, p minus 1 goes to somewhere else. As a set, they are still the same set. And why is that? Why is that? Okay, 0 goes to 0, that's obvious. But the remaining one kind of get jumbled up. So what we're going to prove is, if two numbers, after multiplying by a, become equal, let's prove that I equals j. So basically, I want to prove that this map is injective. If it is injective, then we're done. Because it's injective, it's a finite set, that means it must be bijective, right? You don't even have to show that it's surjective anymore, because injective, same size, means bijective. Okay, but we're talking about mod p addition, so it's the same thing as ai is congruent to aj mod p, then ai minus j is 0 mod p. But a is not a multiple of p, right? A is non-zero, right? Remember? So we can say I minus j must be 0 mod p. It's from the usual properties of integers. And hence I is congruent to j mod p. Or indeed, I can say the mod p element I and the mod p element j are the same in the first place. So that means this map is injective. It permutes the elements. That means one of the elements here is 1. We don't know where it is, but it's somewhere in there. And hence a multiplied by some number is equals to 1. Okay. Does anyone not understand this part? Because it's just going to get more and more abstract from here. So first of all, we've just proven that this set equipped with mod p addition and mod p multiplication is a field, because all of the properties are fulfilled. In particular, the most important one, multiplicative inverses. Let's look at an example, right? Let's say we look at mod 7. Mod 7. Hang on, why is it not working? Okay, mod 7. 0, 1, 2, 3, 4, 5, 6. The mod 7 integers. Now, what is the multiplicative inverse of 5, for example? 5 times what is 1 in this set?
3.
Yep, exactly. So 3 is the multiplicative inverse of 5 in this set. So yeah, so that's what a field is if we use the mod p definition. Of course, these are not the only fields. I'm just talking about one particular example of a field. And this field has a very nice notation. I mean, it's just a notation. Like how the set of real numbers, set of complex numbers have a symbol. This symbol is called f and then p. It's called the finite field of order P, or the prime field of P, or there's many names to it. Okay, so let's talk about the intuitive way of thinking about what a field is. So basically, a field is a set where we can add things, subtract things because of the existence of additive inverses, multiply things, and also divide things because of the existence of multiplicative inverses, except dividing by zero, because zero does not have a multiplicative, well, zero is not required to have a multiplicative inverse here. So what's a field? You can add things, subtract things, multiply things, and divide things, except dividing by zero. So that's intuitive way, but it might be misleading because you are kind of associating it to the usual addition that we have in Q or R or C. So you have to be careful if you want to like be very vague in your arguments. So now we have this new field called FP. And let's look at a few other properties of fields. Again, since it's a completely new abstract definition, we have to make sure that every single property that we prove here is logically accurate, as in we don't say, oh, it works for the real numbers, so it should work for any arbitrary field. We cannot do that because we know the set of real numbers is a field, but there might be other fields out there, right? So for example, for an arbitrary field F, we don't even know whether A times 0 is always 0. Okay, let's say we don't use the bar symbol anymore. We just say this 0 is the additive inverse. We don't even know if A times 0 is 0, and we're going to prove it here. Because how did we define 0? We only define 0 as the additive identity, right? And of course, in terms of the additive inverse, 0 here has nothing to do with multiplication in the definition. So how do we prove that A dot 0 is 0? We have to use this last property. This is the only property that links plus and times together, that links addition and multiplication together. And we will do this by saying, okay, A dot 0 is A dot 0 plus 0, because 0 is the additive inverse, right? Now, by the distributive law, is A dot 0 plus A dot 0. Okay, now we have A dot 0 equals A dot 0 plus A dot 0. Again, we want to be careful. We don't say we can cancel both sides. We say we can add. We say we can add the additive inverse of A dot 0 on both sides. Add the additive inverse of A dot 0 on both sides. Then now, by the definition of additive inverse, this becomes 0. This becomes A dot 0 plus 0, which is A dot 0. So yeah, indeed, anything times 0 is always 0. We cannot use the argument that, okay, anything times 0 is equal to 0 in the real numbers, so it works in any field. No, we have to prove it from basic principles. Okay. And in fact, it will be quite fun if you delve very deeply into this kind of abstract algebra kind of thing. But this will be just a surface introduction of fields. So I won't be proving too much stuff like this. How exactly do you explain line 3 and 4? Which one? This one and this one? Okay, let's see. I'll explain every single step. So the first equality A dot 0 equals A dot 0 plus 0 is due to additive inverses. Sorry. It's due to 0 is the additive identity. Anything plus 0 is itself. So 0 plus 0 is itself. Now, how about the second one? Second one is the distributive law. Well, it's the same thing. You just let B equals C equals 0. Now, how do I get from here to here? Since A dot 0 is an element of the set, it has an additive inverse, right? It has an additive inverse. Now I add the additive inverse on both sides. I add the additive inverse on both sides. Then these two cancel. By cancel, I mean the property that A plus its additive inverse is 0. And then these two become 0. But then A dot 0 plus 0 is itself A dot 0. But the left-hand side is completely 0. Okay, you might be not convinced about the action of adding something on both sides. If you're not convinced, I can also write it like that. I can write it as 0 equals minus A dot 0 plus A dot 0 equals minus A dot 0 plus, remember this thing is equals to A dot 0 plus A dot 0 by the equality above. But then again, you can talk about associativity again. These two add up to 0. This one is A dot 0. But 0 plus anything is itself. So this is A dot 0. That's if you don't like the way of like adding inverses on both sides, but which is actually legit. You can just add anything on both sides. It's a shortcut way of saying what equality is. If you apply the same action to two things that are the same, you get the same thing. Yeah, but let's not talk about this that much. The point I'm making is that you have to prove things from the axioms that you fix at the beginning. It's a very minor thing that I just want to bring out. But let's look at the next property. That is if AB equals AC and A is not 0, then B equals C. Anyone wants to prove this? Try to prove this. You can only use the rules from the 7 axioms of a field. Oh, sorry, the result you want to prove is B equals C. And how do you prove this?
Divide both sides by A.
Yeah, kind of, but we don't want to use the word divide yet, because we want to directly use the rules. So I would say I multiply both sides by the multiplicative inverse of A. Right? If I multiply both sides by the multiplicative inverse of A, then by associativity I can say this is equals to 1, this is equals to 1. 1 times anything is itself, so the left hand side is B, the right hand side is C. Yeah, okay. Okay, so that's all. Now the next one. The next one is quite important. If AB is 0, then either A equals 0 or B equals 0. Well, the contrapositive of this, the completely equivalent statement is, if you multiply two non-zero elements, you must get a non-zero number. Okay, and how would you prove this? So remember, only non-zero elements have multiplicative inverses. So what I would do is, I split into two cases. So if A is 0, Okay, someone said 0 equals A times 0. Well, that will be a backwards statement, right? It doesn't mean if two numbers multiply to 0, one of them must be 0. If you just use the argument that anything times 0 is 0, it doesn't go backwards. I'll show you a case where anything times 0 is 0, but there are two elements that multiply to 0. I mean, that set is not a field anymore, but I will show you that it exists later.
Mod 6.
6. Yeah. If you take, well, let's not talk about mod 6 yet. Let's just focus on this. Yeah. So let's talk about the proving this thing first. So if you're working in a field, why is this property true? Okay, basically I will split into two cases. If A is 0, or if A is not 0. So if A is 0, then we're done. We don't have to do anything because that's the result we want. We're done. If A is not 0, then it has a multiplicative inverse. Exists. So multiply both sides by A to the minus 1. So I get B equals 0 times A to the minus 1. And that's 0, because we already said everything times 0 is 0. So if A is not 0, B is forced to be 0, and hence either A is 0 or B is 0, or both, which is also fine. Again, if you look at this notation that I use, A to the minus 1, this has nothing to do with exponents yet. This has nothing to do with exponents yet. It's just a notation for a multiplicative inverse of an element. So basically what we're doing here is to start everything from scratch, if that makes sense. Okay, this property is quite important, so I'll give it a name. I would say if a set has this property, it has no 0 factors. So 0 doesn't split into two non-zero factors. I'll just say this set has no 0 factors. Okay. There is a nice name for, there is an actual technical name for this. It's actually not no 0 factors. There's a name for this, but I don't want to confuse you. I don't want to confuse you. But if you want to know, it's called integral domain. But you don't have to know that name. Either means A and B can't be both. No. In maths, when we say or, we also include the case where both of them are true. Okay, either I mean it's disputable, so I'll just not write either. Okay, can I say the formal name again? Okay, the formal name, which I will not say again because I don't want to confuse anyone. It's called integral domain. So any set that has no 0 factors is called an integral domain. I will not I will not refer to this name. I will just say a set has no 0 factors, because that's the more that's the more friendly name, because it makes sense. If I say integral domain, you have to think again what integral domain means. So a field has no 0 factors. Again, a field is an integral domain, but yeah. Now let's look at some other sets that is not a field but has 0 factors. So for example, the mod 6 integers, or any mod composite number integers. So 0 to 5. 0 to 5. There are two non-zero elements that multiply to 0. Right? 2 times 3. 2 and 3 are not 0 in this set, but they multiply to 0. So the mod 6 integers, they don't form a field. Okay. So that's a quick way to prove that it's not a field. There are also other ways to prove that it's not a field. For example, not every single thing has a multiplicative inverse. Not every single non-zero element has a multiplicative inverse, basically. Okay. So basically, yeah, so that's about zero factors. So now, let's talk about polynomials and we construct the set of polynomials. For any given set S, I will define this new set S bracket X to be the set of polynomials with coefficients in S. So this applies to any set. It doesn't have to be a field, but of course later we were talking about the case where S is a field. But I'm making a very general definition here. So polynomials with coefficients in S. Okay. Now, if S is a field, so let's say S is F, is a field, arbitrary field, not necessarily the mod P integers, not necessarily the real numbers, not necessarily the complex numbers, just an arbitrary field, any field that satisfies the 7 properties above. Then this set Fx, firstly, it's not a field because the element X, the polynomial X, does not have an inverse. If you multiply X by anything, any other polynomial, you will never get back 1, right? So it's not a field. However, the nice thing is that this thing has no zero factors. So let's try to prove that. It's quite a fun thing to prove also. So assume 2 polynomials multiply to 0. Well, I'll prove the contrapositive, sorry. Assume two polynomials are not 0. Gx are not 0. I will prove that their product must not be 0 at all. So Fx can be written as, I will talk about the leading coefficient, an times x power n plus blah blah blah. Gx, let's say the leading coefficient is bm x to the m plus blah blah blah. By blah blah blah, I mean lower order terms, lower degree terms. And then an and bm are not 0. But n and m can be 0. That's the constant polynomial, right? But these leading coefficients must not be 0. Otherwise, it will be 0 automatically. So now, if we multiply 2 polynomials in the usual way, of course, I define multiplication in the usual way. Fx gx, the leading coefficient is obviously an bm x to the m plus m, and then plus lower degree terms. Now, is this ever 0? No, because an and bm are elements of the field. They are non-zero, and since a field has no 0 factors, this is non-zero as well. And therefore, Fx gx cannot be the 0 polynomial. So this is a very important property of the set of polynomials, is that it has no 0 factors. If you have 2 polynomials that multiply to 0, one of them must be 0. Okay, what's so important about this is because now we can talk about factorization in an arbitrary set of polynomials of some field. So, but before that, let's talk about division algorithm. Division algorithm. So that's what you do in high school, where you have a polynomial here, there's some polynomial here, and then you do long division, right? You write some quotients, subtract, and then in the end you have some remainder. This remainder must have a lower degree, than this quotient. This procedure works perfectly well if you're working in a field as well, because everything has a multiplicative inverse, right? So you just do the same thing, same procedure, same algorithm. So I will not prove this very formally. It's quite obvious why it works if you go step by step, because it's an algorithmic thing. I don't want to jumble up the proof. So works, I'll just write it, works in fields as well. And that means given any fx and gx, I can do long division, creating a division with remainder. So this thing multiplied by qx plus rx, where the degree of r is less than the degree of g. Okay. And q and r are unique, by the way. And why are they unique? I will leave that to you. But a hint is, if you have q1, r1, q2, r2, you have two discrete equations, subtract, factorize, and then look at the degrees. Then you will see that q1, q2 must be the same, r1, r2 must be the same. So that's the division algorithm. What does the division algorithm tell us? The division algorithm gives us this result, the remainder theorem for arbitrary fields. If R is in the set F, fx polynomial is in the set fx, fr equals to 0, so I substitute x by r. If it's 0, that means fx must be the polynomial x minus r times gx. Again, let's not be totally pedantic here. By x minus r, I mean x plus the additive inverse of r. Okay, why is that? Because, well, the simple answer is, because if we do division algorithm, this is a degree 1 polynomial, we will end up with some constant. This constant must be 0 because fr is 0. So that, actually you can call this a remainder or factor theorem, whatever. So that means very important result. In FP, now we refer back to FP. Just now we were talking about arbitrary fields, because I want to talk about the useful things. Now we talk about FP. In FPX, there is factorization. So, and it works very similarly to the usual thing that we know. So if the degree of a polynomial is n, then this equation fx equals 0 has at most n solutions. This doesn't just apply to the set of real numbers, it applies to arbitrary fields. At most n solutions. Why? Because anyone wants to try to say why? It has at most n solutions. If the degree is n.
how about fx is, and the degree of f is 0?
Oh, the degree of f, okay, yeah, I should say f is non-zero here. F is non-zero. But degree of f is 0 means it's constant. And a constant has 0 roots, right? If it's a non-zero constant, of course.
Constant, maybe it's like fx equals to 0.
Yeah, but I say f is non-zero. So if it's constant, so it's like fx equals to 7, maybe. Then such a f has no solutions, 0 solutions. But yeah, I forgot to write here. F is non-zero. But yeah, quite a minor thing. Let me see. Okay, someone said x minus r1, x minus r2. Yeah, so you consider the x minus r's, the factors of x minus r's. If there's one root, r, that means you can factor an x minus r out, right? Like if you keep looking at this equation, if there's a root r, I can factor x minus r out. If there's a second root, that is different from the first root, that means it must be a root of g. Why? Because f has no 0 factors. If the x minus r term is non-zero, but the whole thing is 0, g r2 must be 0, if that makes sense. So if there were a second root, that means r2 minus r times gr2 is 0. But remember, in an arbitrary field, there are no 0 factors. That means gr2 is 0. That means in gx, I can factor out an x minus r2. And then I keep going. I reduce in each step the degree by 1 each time I have a new root. I cannot go on forever. I can only reduce the degree by n times if the degree is n. So that's why I can only have at most n solutions. Okay, does that make sense? So let's look at an application, like the problem in the handout. So let's say, yeah, the first example that I gave. Let's say I have this x minus 1, x minus 2, blah, 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 x minus 101. Sorry, x minus 100, so until 100, let's say. Okay. Now, the coefficient of x squared is very, very troublesome to calculate, right? Coefficient of x squared. Very, very troublesome to calculate. Okay, by the way, this is talking about the regular polynomials, right? The integer polynomials. The coefficient of x squared is very difficult to calculate because if you want x squared, you want like the remaining 98 terms, but then you have 100 choose 98 terms, you want to add them all up. So very complicated. But what if I ask, what is the coefficient of x squared? What's the remainder when divided by 101? In fact, let's complicate this even more. Let's say coefficient of x to the 50. X to the 50. That's even worse than x squared because you want 100 choose 50. I think no one would really go and find a general form for that. I mean, it's theoretically possible, but I don't think anyone would take the time to do that. But let's say we want we want the remainder when divided by 101. Even if you do it mod 101, if you do it the usual way, it's still difficult. You want to take like 100 choose 50 terms and somehow you want to manipulate them, talk about its remainder. Very complicated. But if we bring this into the field fpx, everything becomes much simpler. So let this be fx, for example. Now, when expanded, it has some very long, when expanded, it has like x to the 100 plus blah, 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 blah. Now, if I bring this into fpx, sorry, I don't want fpx, I want a very specific one, f101x, because 101 is prime. So bring this polynomial into f101x. Now, then 1 becomes the mod 101, well, the 1 mod 101 integer, 2 becomes the 2 mod 101 integer, 100 becomes the 100 mod 101 integer. So we have, if you want to write this very, very, very clearly, let's do this. Let's say it's A99, X99, plus until A0. If I bring this into F101, then it becomes X100. Remember, the powers don't get modded, by the way. The exponents, they are always positive integers, not negative integers. We don't take mod on those numbers. Then A99 gets modded. Modded, I mean, it gets taken into mod 101. And so on until A0 mod 101. And then this is X minus the mod 1, the 1 mod 101 number, X minus 2, blah, 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 X minus 100. You might think, okay, this doesn't really help, but let's think of a polynomial. Let's think of a polynomial that has roots 1, 2, 3, 4 until 100 and has degree 100. So I'll give you a hint. Fermat's-Tito theorem again. So remember, Fermat's-Tito theorem says that a to the 100 is always equals to 1 mod 101, right? Well, if a is non-zero or not divisible by 101. That means x to the 100 minus 1, this polynomial has roots 1, 2, 3, 4 until 100. And it has 100 roots. That means those two polynomials must be the same, right? Those two polynomials must be the same. But if it's not the same, you can subtract and then talk about degree 99, and then you have 100 roots. But anyway, it must be the same. You also have to consider the leading coefficient, by the way. But we can say this is equal to this because we study the roots. So it's not because we expanded anything, we're just studying the roots. Very convenient thing. Study roots. Wow, then that simplifies everything. This polynomial is the same as this. That means everything here is 0. And this thing is minus 1. I mean like minus 1 mod 101. So that means the coefficient of x to the 50 must be a multiple of 101. Because after I take it into F101, it becomes 0. And in fact, every single coefficient in the middle here becomes 0. They are all multiples of 101. Does anyone not understand what I'm saying here? If you do understand, okay, wait, can you repeat why the two polynomials are the same? Okay, you mean this one and this one? You mean these two, right? Okay. So by Fermat's-Tito theorem, any non-zero residue to the power of 100 equals 1. So that means this polynomial has roots 1, 2, and then so on until 100. They all satisfy this thing to be 0 after plugging in. Then I can say it this way. This polynomial has a factor of x minus 1. I factor it out. Then I factor x minus 2 out. I factor x minus 3 out. Factor x minus 4 out until x minus 100. But once you do that, you already have 100 factors. But the degree of x to the 100 minus 1 is 100. So it must be, after factoring everything out, you have nothing to factor anymore. Does that make sense? Like, okay, x to the 100 minus 1 equals x minus 1 times something. Because 1 is a root, but then 2 is also a root. So I can factor x minus 2 from G. But I keep factoring until I get x minus 1, x minus 2. Hang on. Yeah, and then until x minus 100 times some polynomial. But this polynomial can only be a constant now. From polynomial zx. This polynomial must be a constant now by comparing the degrees. Well, it must be 1 by comparing the leading coefficients. So these two polynomials are the same. And yeah, so now you can conclude everything in the middle is 0 and the thing at the back is minus 1. Anyone else does not understand this? Can you explain the line above the study the roots? Oh, okay. So the first equality, basically, you mean? I take this polynomial, which is, I'm sorry for using red here, by the way, I'm just trying to use a different color. This polynomial x minus 1 until x minus 100. Let's say its expanded form is like this, x to the 100 plus a99, x99, and so on. So I label the coefficients as a1, a2, a3, blah, blah, blah. Now, if I take, well, these two expressions, which should be the same, into mod p, that means I take every coefficient mod p. I take every coefficient mod p. Well, this one becomes this. And this one becomes this. So those two are the same thing. Because before that, they are the same. After I take mod p, they should be the same. I just replace every single number here by the mod p equivalent. Okay, you're welcome. So if you've never heard of this technique, it should be quite mind-blowing to you if you understand what I'm saying. Because suddenly you can determine the remainder of everything in between mod 101. And then a0 is minus 1, mod 101. Of course, it doesn't just work for 101, it works for any prime. It works for any prime. So this also obviously gives us another proof for Wilson's theorem. If you remember what that is, Wilson's theorem says p minus 1 factorial is minus 1 mod p. Wilson's theorem. How does it follow from the proof above? We just look at the constant term, right? The constant term is 100 factorial, well, times some power of -1. But then you can sort that out. Then that thing is equals to -1. Yeah. So by taking polynomials into mod p, you can somehow simplify things a lot. But you have to remember that you know what you're doing. Like, you know what you're doing. You take something in zx and then bring it to fpx. Okay. Let's look at something else, which is also an application, something called Eisenstein's criterion. Eisenstein's criterion. So it is a criteria for irreducibility, but it's not a necessary condition. It's just a sufficient condition. So if the condition of this criterion are met, then you can say that polynomial is irreducible. But it doesn't go the other way around. Okay. So if xn, an xn plus blah 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 plus a naught is an integer polynomial, it's an integer polynomial, and the following properties are satisfied. So P does not divide an, but P divides everything else. P divides everything else. But P squared does not divide a naught. So basically the VP of a naught is 1. Then this is irreducible. It's an irreducible polynomial. You cannot write it as a product of two linear integer polynomials. Well, given the conditions here, you can probably see how simple this polynomial would become after taking mod P, right? So let's say that fx is gx times hx. Gx times hx. So all of these are integer polynomials. We haven't brought them into mod P yet. If we bring them into mod P, what does fx become? It becomes an mod P. But then everything else vanishes because they are all multiples of P. They all become 0. Okay. And then G becomes some reduced polynomial, which I will call G bar. And then H becomes some reduced polynomial, which I call H bar. So this is bring into fpx. The word bring into is quite vague also. There's a technical name for this in abstract algebra, but I'm resisting the urge to say it because it's a very complicated word. But if you're interested, it's called homomorphism. Yeah, so let's say this thing is this. Now, what can we say about G bar and H bar? G bar and H bar. Well, the left hand side is just some power of x. So surely we can talk about, like, we can say that G bar and H bar, they are powers of x as well. But we have to be a bit more careful than that because remember, things can sum up to 0 in the lower terms. But we can talk about it in terms of the roots, for example. So 0 is a root on the left hand side. So 0 is a root on the right hand side. That means x divides one of the polynomials. And then I divide by x, I repeat the same argument again, In each step, the x either goes to G or H. In the end, I can conclude that G bar x is some constant times a multiple of x, and then hx is a multiple of, let's not use d, let's just use something else, m, and this is d x to the n minus m. I should repeat what I said just now. The factor of x should divide into one of these two. So, but whenever it divides into one of them, I just divide both sides by x. repeat the same argument. Then the x kind of go into g, sometimes go into h, g, h, g, h. By the end, we exhaust every single x. That means g has received some power of x, h receives some power of x. Okay, so g is like this, h is like this. Remember, if you're not clear about anything, please immediately say. Otherwise, I will continue. So g is like that, h is like that. But okay, that means what should the original g be? That means the original g should be something like c times xm plus some multiple of p, times lower terms. So the lower coefficients, they are all multiples of p, right? Multiples of p. I don't know how to write it in a simpler way, but yeah, so the lower coefficients are all multiples of p. Hx is d times xn minus m plus multiples of p for the lower terms. Is that possible? Let's look back at the condition. P squared does not divide the constant term. But if g and h are non-trivial polynomials, the last term of gx is a multiple of p, the last term of hx is a multiple of p. That means the constant term of fx is divisible by p squared. So that's a contradiction. Okay. Any questions? Any questions? Okay, if not, let's move on. Now, we're going to build higher layers of abstraction. So given a field, an arbitrary field, I can actually add something into it. I insert some new element, some foreign element. Then this set will blow up into a larger, okay. There is a question here. For the question we discussed previously about x minus 1, x minus 2, 1 to x minus 100, what can we conclude? Let me go back to that. Wait, that's all the way down here. What can we conclude? What we can conclude is A99 is a multiple of 101, A98 is a multiple of 101, until A1 is also a multiple of 101. Because all of these vanish under mod P. As you can see, the middle terms, there are no middle terms in x100 minus 1. So the conclusion is that A99, A98, blah, 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 these are all 0. And then this thing is minus 1. Yeah, okay, you're welcome. So let's get back to the new section. Given a field, I can insert something into it. It will blow up into some larger field. So let's see. Let's look at a familiar example. Okay, let's make our lives easier. Start with a simple example. This example is not in the handout, but let's say we start with Q, the field of rational numbers. The field of rational numbers. Remind yourself that this is a field because every non-zero rational number has an inverse, right? P over Q becomes Q over P. So Q, well, first of all, if we only know about Q, let's say we don't know about the set of real numbers, right? That means we don't know square root 2 exists. We don't know that square root 2 is 1.414, blah, blah, blah. We don't know this thing exists. But let's just say that let square root 2. So now this is just a symbol. This is just a symbol, square root 2, be a root of x squared minus 2, which is a polynomial in Qx. And this is an irreducible polynomial. You cannot factor this anymore. You cannot factor this anymore. Now I insert this new number into Q, but I want it to be a field, right? If square root 2 suddenly sneaks into Q, like an imposter, it just goes in. If square root 2 is inside, 1 plus square root 2 is inside, 2 plus 3 square root 2 is inside. In fact, any number in the form a plus b square root 2, where a and b are rational numbers, must be inside if we want the resultant thing to be a field. So square root 2 goes inside. Now this Q becomes a larger Q. Are these everything that we need for it to be a field? And surprisingly, the answer is yes. If I define this set, I give it a new name. I call it Q square brackets square root 2. This is a larger field than Q, a smaller field than R. This is a field. Why is it a field? Okay. Actually, this is a fun exercise to do to prove that it's a field. So if we add two things in this form, we obviously get another number of this form. If we subtract, same thing. If we multiply two numbers of this form, remember that square root 2 is a root of x squared minus 2. That means if I square this element, I get 2. So hopefully you can see that if I multiply two numbers in this form, I should get some, you just expand everything, collect the rational terms together. You should get some rational number plus another rational number square root 2. Hopefully you can see that. Hopefully. Now, the most stringent property for a field to hold is the multiplicative inverse property. And does it hold for this? Let's see. Can we talk about the inverse of this? Does such a thing exist? And apparently, yes, we can. Because let's say if we multiply up and down by the conjugate, the bottom bit, the denominator, is some rational number, right? Is some rational number. Oh no, it's very laggy now. A plus b squared 2. The bottom bit is a squared minus 2b squared. And then it's b over a squared minus 2b squared. So inverses exist as well. Inverses exist as well. Very interesting. Okay, of course, by the way, you might ask, what if the denominators are 0? But if they were 0, that means 2 is square root 2 is a rational number, right? So there aren't 0. And indeed, there are inverses. Because this is a rational number, this is a rational number. So this is indeed a field. This is indeed a field. So let's look at what we did just now. What we did is we actually added some new root of some irreducible polynomial, added into it. Now suddenly we can construct a new larger field. And why must it be irreducible? If it's like reducible, this I won't explain it much here, but if it's reducible, basically the resultant set won't be a field. There won't be multiplicative inverses for every single term. this is very deep abstract algebra stuff, so I won't go deep into it. But if you want to know kind of the surface level of explanation, you can look at the footnote of my handout on that page where I talk about constructing larger fields. There's a small footnote, there's a small sentence there. You can kind of read it, even though it doesn't really explain much, but at least there's an analogy there. Okay. So that's the procedure of adding new elements into it. Of course, this kind of thing actually gives birth to a new field of mathematics, something called Galois theory, which again is a very interesting thing, but totally out of what we're gonna say now. But let's look at like the example given on that page. So section 2, building larger fields. It's kind of the same thing. If you look at, I'm not gonna write it down anymore because it's kind of the same thing as the example we did just now for Q. So consider F7, x squared minus 3 is irreducible. So you can let square root 3 be a new element that is a root of x squared minus 3. And then you just talk about a plus b squared root 3. Same logic. Then you get a new set. But of course, F7 square root 3. Can anyone tell me how big this field is? Like how many elements are there here? F7 has 7 elements, right? F7 has seven elements. F7 has 7 elements. How about this one? How many elements are there? Remember, a plus b square root 3. A plus b square root 3. And a could be any mod 7 integer, b could be any mod 7 integer.
49.
Yes, thank you. So it's 49, 7 squared. This is also a field. In fact, there's a theorem that says that the sizes of any finite field must be a power of a prime. 0 plus 0 square root 3 is the same as 0, right? Yeah. 0 plus 0 square root 3 is the same as 0. So it's basically like you choose a number for A, choose a number for B. 7 choices. Yeah, okay. But of course, for the Q example, it's not very interesting because Q is infinite. Q squared 2 is also infinite. Okay, so that's F7 square root 3. But we cannot add square root 2 into F7. Why? Because there's already a sort of square root 2 inside this set. What is it? 4 squared, right? 4 squared is 2 in mod 7. 3 squared also 2 mod 7. So if you add square root 2 into F7, it is still F7. It didn't really enlarge it at all. Okay, now let's skip section 3 first, the IMO example, because before we look at that example, we have to kind of prove something in problem 1 of the exercises. So section 4 exercises problem 1. If F is a finite field, F is a finite field, then X to the F minus 1 is equal to 1. Again, after all of this, mod P whatever, I did this kind of bar thing on top of each number to just tell you that this is a mod P number. But if you're really comfortable with it, I will just not write the bar on top. If you are quite sure in which case you're talking about regular integers, in which case you're talking about mod P integers. So again, there's this flexibility in notation that you can use. But But keep in mind that you know what you're doing, and that's what's sufficient. So if F is a finite field and X is a non-zero element of the field, non-zero element of the field, then X to the F minus 1 equals to 1. Like this, again, there's this flexibility in notation here. This one, I'm talking about the additive identity of the field, which I should have written 1F, but I'll just write 1. Who cares? So this thing is true. It's kind of like Fermat's-Little theorem, but more general. Because Fermat's-Little theorem is just where F is Fp, right? But if F is a finite field, this is true. Why? Why? Does anyone remember how to prove Fermat's-Little theorem? Does anyone remember that? Anyone? I'll give you a hint. It's something to do with what I'm showing here. Complete residue system. Yes. So if you want to prove Fermat's-Little theorem, you take that P minus 1 non-zero residues, right? If you multiply by A, remember it permutes every single residue. That means the product of the residues before must be the same as the product after. But if I multiply every single element here and is equal to every single element here, there's this extra factor of A to the P minus 1 at the bottom, right? A to the P minus 1 at the bottom. And then like 1 times 2 times 3 and so on. But then these are all non-zero residues, non-zero elements in this field. So I can cancel them off if they are equal. Remember the cancellation law, AB equals AC, which coincidentally is also on this screen. AB equals AC means B equals C. So A to the P minus 1 is 1. It's definitely 1 because I can cancel both sides. So how do we apply this here to a general field, a general finite field? Look at the power. It's size of F minus 1. Kind of completely the same thing as that. So the answer is you just consider the F minus 1 non-zero elements of that field, right? And then you multiply everything by X. It must permute the elements by the cancellation law. It is injective. And then you do the same thing, if that makes sense. Should I write this down? It's like the same thing as Fermat's-Little theorem. But instead of 1 to P minus 1, I just take the F minus 1 non-zero elements that we don't know what labels they have, but they are non-zero. So it's like 0, and then I don't know, A1, A2, blah blah blah, A F minus 1. Multiply everything here by X. That means the product of the non-zero residues. I don't multiply 0 into it. If I multiply 0 into it, everything goes to waste. Everything becomes 0. And then I multiply every single product here. There's an extra factor of X to the F minus 1. So that means it must be 1. Right. There are other ways to prove this, of course. There are other ways to prove this. Now, if x to the n equals 1, and n is the smallest positive integer that works, smallest positive integer, then we call n to be the order of x. The order of x. If you want to be very pedantic, then the order of x in this field F. But if it's clear, you can just say order of x. Now, then why does n divide f minus 1? Why does n divide f minus 1? So the order of x must divide the size of the set minus 1. Why is that true? Because by definition of order, it is a smaller such power. Well, what if like x3 equals 1, x3 equals 1, but then x10, but then the size of the set is 11, so x10 equals 1. How does this break the rule that 3 is the smallest? How does this break the rule that 3 is the smallest? But let's say I say 3 is the order, but then the size is 11. Now 3 does not divide 10, right? What happens? What happens? X to the 3 equals 1, x to the 10 equals 1. Remember, in fields, we can safely talk about cancellation, as long as it's not 0, which I assume here, x is not 0. So you can say like x to the power of 6 is 1, x to the power of 9 is 1, right? But if x to the power of 9 is 1, x power 10 is 1. That means x is 1, right? Cancellation law. Well, by cancellation law, I mean AB equals AC implies B equals C. I cancel the x's, I get x equals 1. But then 3, you said it was the smallest. It's not the smallest anymore, it's suddenly a 1. So contradiction. And that's how basically you define that's basically how you prove for the general case. If n does not divide f minus 1, do the division algorithm, write f minus 1 as a multiple of n plus some remainder, and then say that now the remainder is suddenly a smaller number than n. So that's a contradiction. So it must be dividing f minus 1. Okay, does that make sense? Anyone does not get it? Okay, if everyone's okay, let's dive into that IMO problem 2003. It's apparently an N7, but if you know field theory well, it's quite fun to read the solution. Wait, how do we generalize the proof just now? Well, you look at how 3 and 10 interact, because I say 3, 6, 9, right? And then suddenly this difference is less than 3. If n does not divide f minus 1, I just keep taking multiples of n until I'm like less than n. The distance is less than n from f minus 1, and then just cancel. Or more concretely, you can say write f minus 1 as nq plus r, right? And then take both sides to the power of, as the power of x. And suddenly you can prove that xr equals 1. but r is less than n, so there's a contradiction. Yeah, so unless r is 0, which is when they divide each other. Okay, where were we? Okay, so the IMO problem. So read it first. Read it first. I'm not going to write the whole problem on the board again. Read it carefully. So it's a recursive relation where the next term is the previous term times 2. Sorry, the previous term squared times 2 minus 1. Very uncommon recurrence, because normally we talk about linear recurrences, but this is obviously not a recurrence relation. But in the theory of recursions, you can actually find the recursive form quite easily, because if you look at 2x squared minus 1, it kind of reminds you of the cosine function, right? The double angle formula for cosine. So here I kind of vaguely went through the process to get the general form, because that's not the topic of this chapter. I'm talking about what comes after it. So cosh x, just a very brief introduction. Cosh x is e to the x plus e to the minus x over 2. And apparently it kind of obeys the double angle formula as well. So once you do that, you can kind of simplify an to a general form, because you will find that the x just doubles each time you move forward by 1 on the sequence. So that's an exercise by itself. That's the theory of recursion. That's not our topic today. That's more of an algebra topic. So assume we have the form given. So well, just given 2 plus square root 3 2 plus square root 3 to the power of 2 to the n plus 2 minus square root 3 to the power of 2 to the n. How do we compute this thing mod p? Because first of all, there's this square root 3, right? Square root 3 is kind of like an irrational number. Why is it here? But what we do know is that when expanded, the square root 3 terms must cancel out, right? The square root 3 terms must cancel out if there are remaining square root 3 terms, because we know an is an integer. So why not we just treat square root 3 as some abstract element whose square is 3? So does that remind you of the section just now where we enlarge the field? And that's exactly what we're going to do. But of course, square root 3 sometimes is itself an element of FP, sometimes it's not. So we have to split into 2 cases. So if you look at case 1, in fact, I think I should just switch this screen to directly to this handout, because I will be writing exactly the same thing. Yeah, so let's look at this. Okay, let's look at this. Where is the draw function? If x squared minus 3 is reducible mod p, again, I'm being flexible in the notation here. I should have written 3 bar, but let's just say we are comfortable with it already. X squared minus 3 is reducible mod 3. We treat square root 3 as the root, right? So square root 3 is already in FP itself. It doesn't matter because we know its square is 3. So treat that square root 3 as that mod p integer, which is kind of weird. That's why I wrote this bracket. So since p divides an, because it says if an odd prime p divides an, then 2 to the n plus 3 divides p squared minus 1. So if an odd prime p divides an, then the numerator is 0 because p is an odd prime. The 2 has no place here. So I have this. Now, multiply both sides by this. That means this becomes to the power of 2 to the n plus 1. This becomes 1, right? 2 plus square root 3 times 2 minus square root 3 is 1. You can expand that out yourself. So that means this thing is minus 1. This thing is minus 1. Okay? Now, here is something that I didn't really prove, but let's think about this. Why is 2 to the n plus 2 the order of 2 plus square root 3? Why is it the smallest integer that works? Why is it the smallest integer that works? Look, if you have a smaller number that works, right? If you have a smaller number that works, okay. Remember that if xm equals 1 and xn equals 1, then x to the GCD of mn is also 1. This is kind of like the remainder algorithm just now, the division algorithm we did we did just now. By adjusting the how many times we add the multiple of m, how many times the multiple of n, we can get the GCD. So if the order of this number is n, if the order of this number is d, that means 2 plus square root 3 to the power of GCD of d and 2 to the n plus 2 is 1. Okay. But notice that this means d must divide 2 to the n plus 2. Otherwise, we will get a number smaller than d. We get another order smaller than d. So d divides to the n plus 2. That means the order must be a power of 2. It must be a power of 2. But can it be a smaller power of 2 than 2 to the n plus 2? No, because if a smaller power worked, that means its power to the 2 to the n plus 1 would never be minus 1 anymore. It will be 1 if the order were a smaller power of 2. That thing will become plus 1, not minus 1. So hopefully you can get that. Hopefully. So 2 to the n plus 2 is the order of 2 plus square root 3 in FP. So therefore, 2 to the n plus 2 must divide FP minus 1. Remember, but this problem 1 of the exercises just now. But then I just multiply both sides by p plus 1. P plus 1 is an even number. So 2 to the n plus 3 divides p squared minus 1. Okay, that's this case where square root 3 is actually a residue in mod p. Now, if it's reducible, if it's irreducible, that means square root 3 doesn't exist. We can work in the enlarged field fp square root 3, which I forgot to write p there, but never mind. So if you repeat the same steps again, you will get that the order is still 2 to the n plus 2. So that's fine. So never mind that. Just repeat everything before. This gives us that 2 to the n plus 2 divides the size of the field minus 1, which in this case directly gives us p squared minus 1. But that's not enough, right? We want 2 to the n plus 3 to divide p squared minus 1. That's the result we want. So we're kind of stuck here. So the strategy is and this is what makes it an N7, is to find some other element u, such that u squared is 2 plus square root 3, such that u squared is 2 plus square root 3. So basically the square root of 2 plus square root 3. If we manage to find such a u, then the order of u will be 2 to the n plus 3 instead now, because you have to multiply by another 2. So the new goal is to find the square root of 2 plus square root 3. And that itself is quite hard as well. This is how we do it. Notice that 4 plus 2 square root 3 is 1 plus square root 3 squared. So if you want to find the square root of 2 plus square root 3, we have to find the square root of 2. We have to find the square root of 2. Or square root of 1 over 2, that's also fine. But in this recursion, an is 0, right? Because p divides an. But an is also defined to be the recursive relation 2 times the previous term squared minus 1. That means the previous term squared is 1 over 2. Hence, that's done. Very hard problem. I chose this not because all such problems involving FP is hard. No, because I want to demonstrate a hard example so that you can get the most of it. Like, you can learn most things from it. The exercises below here are much simpler than the problem on top here. Okay, so any questions before we move on to the final exercises? If you have a question and you want to refer to a line here, I'll just label the lines 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if you want to ask a question, you can just refer to which line. No one? Okay. Okay, then let's try a few exercises. Okay, so let's try the second one. If p is larger than 3, a prime, then p squared divides the numerator of this complicated fraction, 1 over p plus 1 over 2 plus until 1 over p minus 1. Okay. We don't really have much time, so I'm just going to start. Anyone has any idea, any suggestions? Like, first of all, how about if we simplify the problem into p? P divides the numerator of this. Well, it's the same thing as doing what? If I take this thing mod into FP, it's possible, right? Because 1 to p minus 1, they are all invertible. And if we prove that this is equal to 0, then we're done in FP. That means p divides the numerator of this fraction. But in FP, this is easy because in FP, this is 1. This is 1 over minus 1. This is 1 over 2. The second to last is 1 over minus 2. So they all cancel out, right? They all cancel out. The result is 0. So at least the numerator is a multiple of p. But that's not enough, right? We want p squared. And modding p squared doesn't help. And in fact, the mod p squared integers do not form a field. So that's also quite disappointing as well. The mod p squared integers do not form a field, even though the size is p squared. So the trick is we're going to do some Gaussian pairing. So again, we match these two like that. So let's multiply by 2. So this is like 1 over k plus 1 over p minus k. K equals 1 to p minus 1. This is, there's a p on top, k, p minus k at the bottom. And then I have this, right? So I successfully manually brought out a p. I brought out a p. Now what's remaining is to prove that the numerator of this is a multiple of p. The numerator of this is a multiple of p. And here we can do fp, right? fp, bring into fp. This thing is equal to, well, bring into fp. This thing is equals to 1 over 1 minus k squared, right? 1 over 1 minus k squared. Or I can say just minus 1 over k squared. Because p is 0 mod p. Now, this is hard to sum, but in a field, if you invert the elements, it is still a permutation of the elements. Remember that? If you invert the elements, it's still it's again a permutation of elements. It's a bijection basically. So this is actually the same thing as in FP. Remember, we're working in FP now. The same thing as k squared. Same thing as k squared. If we invert, same thing. Invert, same thing, permutation. But this, we know the formula to this, right? This is p minus 1, p 2p minus 1 over 6. And if p is larger than 3, these two will be responsible to cancel 6. And hence, it is always a multiple of p. Hopefully you can follow. Hopefully. Okay, problem 3, I will not go through. It will be similar to what you did here in N7. You can kind of see how it works. But I'll give you something general, just in case you doubt your answer in the end. This thing doesn't matter. I can change 2p to any natural number n. Any multiple of p squared minus 1 works. That Fibonacci number will be divisible by p. So I don't know why they chose 2p. Okay. And problem 4 is to, well, use something called, it's basically it's actually an application of Eisenstein's criterion, but you have to modify it a little bit for this to work. Eisenstein's criterion says you want a prime p to kind of divide every single term after here, and then p squared does not divide this. But this obviously is not true for it. Obviously not true for any kind of p. The trick is to switch from x to x plus 1. If you switch from x to x plus 1, and you expand, hopefully you can, you would get that the coefficients are all multiples of p. And then it will satisfy Einstein's criterion. But there's also a clever way to substitute x by x plus 1, because if you do it manually, you have to sum a lot of things. Is to also write this as x to the p minus 1 over x minus 1. And now I substitute x into x plus 1 in this form, and it would be much simpler. Okay. It will be much simpler like that. Okay, the last problem is also quite fun. The last problem I'll give you guys as exercise. I won't spoil it. It's doable. It's quite doable if you understand the fields here. It's quite fun as well. So for the last 5 minutes, probably some ending words or whatever. What I'm doing here is a very surface level exploration of abstract algebra. So if you are interested to learn more deeply about fields and other related structures, you can find some nice books to read about it. Personally, there's a book called Algebra. The title is just, well, Algebra by Michael Artin. It's a very concise book, very, very good, but it's quite advanced. So it's also a very good book on fields as well, but it's a book on abstract algebra. So it does talk about groups, rings, fields, integral domains, other things. Yeah. And also I've been quite casual in talking about these elements that you can also have a very formal, well, construction of all of these concepts. For example, this one here, like why is it reducible? Why is it necessarily to be irreducible? Well, as you can see here, if we're basically taking fx mod some irreducible polynomial, it's like z mod p. It's like integers mod prime. But here is like fx mod some prime in the polynomial sense. So that would be an irreducible polynomial. So this is what undergraduate mathematics would look like if you plan to study maths. So you will study a lot of what we call abstract concepts. So it doesn't have to be related to the usual sets that you know. So you set up some fixed axioms. And now suddenly you have a set whose elements are completely unlabeled. You basically say these elements satisfy these properties. That's all. You don't say you can write it as a vector or a matrix or whatever. So yeah, it's you also have to kind of get used to this slowly. It's not really an essential thing to know in Olympiad level, but if you know, it does simplify a lot of things. Like all of these problems are all Olympiad level, by the way. And you can also talk about other structures. For example, I haven't talked about primitive roots. If you also read that book, Algebra, you also talk about primitive roots. And basically it says that for a finite field, its multiplicative group is a cyclic group. That means there is a primitive root. But of course you have to prove that as well. So any questions before we end the class? We still have 1 minute left. Are fields just 1D vector spaces? Yes, yes, they are. In fact, if you want to talk about vector spaces, you have to talk about a field. So for a vector space, like remember we have column vectors. These are the more of the practical kind of vectors. But if you want to abstractly define vector spaces in mathematics, which we do, just like how we define a field here, is to say a vector space is a set where each element can be scaled by a scalar. This scalar is referring to an element of some field. So I'm just going to write this down because it's quite nice. So V is a vector space. But when you say vector space, you must say a vector space over something. And this set will be the set of scalars. And we always require it to be a field. So if U and V are in V, then AU plus BV is in V for all A and B in F. So of course, U and V are kind of like elements of V, A and B are kind of like field elements. And when we talk about vectors, the scalars is basically the elements of a field. So not only you can talk about vector space over R, which is what we normally think of vectors, right? We talk about Euclidean space, 3D space, 2D space. We talk about vectors. Those are vector spaces over R. You can also talk about vector spaces over F2, for example. This is the binary field, or the mod 2 field. And in fact, there are some combinatorics techniques that use vector spaces over F2. I'm not sure if you're going to learn it this chem or next chem, but eventually you will. So yeah. And if a vector space over F is one-dimensional, then the vector space has the same structure as F itself. So you are right. Fields are just 1D vector spaces. But same structure, again, there's a nice name to it. It's called isomorphism. But okay, yeah. So I went off topic just now for the last few seconds. So if there's no questions, any other questions? It's past 1 already. So if you want to leave, you can leave. Okay, if not, then I'll just end the class here. So good luck for your test. I'm not sure when is it, but good luck. Then I say goodbye then. Bye. See you next camp, I guess.
Thank you.
Welcome.